Imagine trying to run a marathon while carrying like a grand piano on your back.
Oh man, that sounds absolutely brutal.
Right. Well, that is essentially what your computer, your smartphone, or really any digital device is doing
Mm.
every single time it tries to perform complex mathematical multiplication on a silicon chip.
Yeah, it's doing a lot of heavy lifting.
Exactly.
Right.
It's exhausting, it drains battery power, and it generates just a massive amount of heat.
Oh, absolutely.
So, welcome to the deep dive. Today, we are unpacking a brilliant 2026 presentation by a developer who goes by the handle at Luck036. And this presentation is titled Direct Form versus Transpose-Form, Multiplierless FIR Architectures.
It is quite the title for sure.
It really is. But our mission for you, listening right now, is to figure out how we can trick computers into doing that incredibly heavy math, without actually multiplying anything at all.
Which is honestly, that really is the holy grail of hardware design.
Yeah,
Yeah, because, well, we tend to take multiplication for granted when we're writing high level software, you know? You just type an asterisk and you just move on.
right. The computer just handles it.
Exactly. But down at the bare metal silicon level, a multiplier circuit is the equivalent of a sprawling, heavy industrial factory.
Like it literally takes up physical space on the microchip.
Oh, massive amounts of space, or what we call area on the chip.
Mhm.
And it consumes a tremendous amount of electrical power. Plus, like any massive factory, it produces a lot of thermal exhaust.
Which is the heat that drains your laptop battery.
Precisely.
Okay, let's unpack this.
Right.
Because to understand how we replace that factory, we first need to look at what we're actually building.
Right.
So the presentation centers on something called a finite impulse response filter, or an FIR filter.
Yes, the classic FIR filter.
And in the world of digital signal processing, these filters are basically the unsung heroes of modern technology.
Hmm.
Like they clean up noisy audio signals, they process high definition images, they manage all the chaos of wireless communications.
Yeah, they are literally everywhere. And the standard way an FIR filter works is by taking a sequence of incoming data points, right? And then multiplying them by a specific set of numbers called coefficients.
Okay.
And after that, it just adds all those results together to get an output. So it is essentially an avalanche of continuous multiplication.
Wow, okay. And the presentation points out that if you have, say, a 32 tap filter, meaning it has 32 of these coefficients, it needs to process at any given moment a generic standard hardware design would require 32 physical multiplier circuits.
Yes, 32 complete factories.
That is 32 grand pianos you are forcing your silicon to carry at all times.
Which is completely unsustainable, if you were trying to build something fast or cheap or battery powered.
Right, you just can't afford it.
Exactly. So the presentation introduces this foundational magic trick to eliminate the multipliers entirely.
I love a good magic trick.
It's a great one. It starts with changing the very way the hardware represents numbers. So we move away from standard binary to something called CSD, or canonical sign digit format.
Yeah, and I can say I found the mechanics of CSD completely mind-bending when I was reading this.
It takes a minute to wrap your head around, for sure.
Because instead of standard binary, CSD uses only 3 digits. It uses +1, -1, and 0.
Right.
And it comes with this strict mathematical rule where no 2 consecutive non-zero digits are allowed.
Yeah, you can't have a +1 next to a -1 or another +1. There has to be a 0 in between.
Which just sounds so strange at first.
It does, but the reason that rule exists is entirely about exploiting hardware architecture. You see, in the physical wiring of a microchip, shifting a binary number to the left or right is practically free.
Like it doesn't cost any power.
Right, it doesn't require a factory. It just requires wiring the output of one thing to the input of the next thing over.
Oh, that makes sense.
Yeah, if you shift a binary number 1 position to the left, you've essentially multiplied it by 2. If you shift it twice, you've multiplied it by 4.
So, let me try to put a visual on this for the listeners
Yeah.
because the math is honestly a little tricky.
Go for it.
Okay, so it's like instead of buying a 32 pack of sodas,
Right.
which represents a heavy, expensive multiplier.
Right, a huge, bulky package.
Exactly. You realize it's cheaper and faster to just grab a 30 pack and a 2 pack and push them together.
Oh, I like that.
Yeah, so those 2 smaller, easier packages represent the simple shifts and adds. You still get your 32 sodas, but you completely bypassed the struggle of finding and hauling that one massive 32 pack.
That is actually a brilliant way to conceptualize it. In hardware terms, instead of a massive multiplication, you do a large positive shift, the 30 pack, and maybe another smaller shift, the 2 pack, and just add them.
Right, just push them together.
Exactly. By translating a coefficient into CSD format, every +1 becomes a positive shift, and every -1 becomes a subtraction.
So you've effectively dismantled the heavy multiplier circuit and replaced it with just like simple shifts and adds.
You've demolished the factory. But the developer doesn't actually stop there.
No, they don't, which is crazy.
Right. Once you've broken these 32 multiplications down into a series of shifts and adds, they introduce a second layer of optimization.
Oh, the cross CSE.
Yes. Cross CSE, which stands for Common Subexpression Elimination.
Common subexpression elimination.
Yeah, and the underlying logic of CSE is just pure pattern recognition.
How so?
Well, when you break 32 different coefficients down into CSD form, you are inevitably going to create overlapping patterns.
Because you're only using +1, -1, and 0.
Exactly. You might have a specific sequence of shifts and adds that appears in, say, coefficient number 3, and then that exact same sequence appears again in coefficient 18.
Oh, I see. And maybe again in coefficient 29.
Exactly.
So rather than building the physical hardware to calculate that same pattern 3 separate times, cross CSE is like this algorithm that scans across the entire filter, finds those shared patterns, calculates the result exactly once, and then just routes that single answer to wherever it's needed.
It just wires the result around. It's incredibly efficient.
The developer even includes the specific formula the algorithm uses to score and rank these patterns, which I thought was really cool.
Oh, yeah, the scoring system.
Yeah. It says the score equals the number of non-zero digits -1 multiplied by the occurrences -1.
Right. And let's break down the mechanics of that formula because it really is elegantly simple.
Yeah, please do.
So, number of non-zero digits is essentially how many additions or subtractions are happening in that specific pattern.
Okay, that makes sense.
And why subtract 1? Well, if a pattern only has one non-zero digit, there's actually no addition happening at all.
Wait, really?
Yeah, it's just a raw number being shifted. There's no mathematical operation there to save.
Oh, right, because you need at least 2 things to add them together.
Exactly. And then why subtract 1 from the occurrences? Because if a pattern only occurs once, well, sharing it doesn't give you any mechanical advantage.
Because there's no one to share it with.
Right. So the algorithm is mathematically hunting down the most complex, most frequently repeated patterns to aggressively minimize the hardware footprint.
It's basically optimizing the optimization. And I was looking at the math in the presentation, and the results of that algorithm are just staggering.
They really are.
Because for a standard 32-tap filter, using just the CSD shifts, you would normally need about 110 physical adders or subtractors on the chip.
Which is already better than 32 multipliers, but still.
Still a lot. But then when you turn on this cross CSE optimization, finding and sharing those high-scoring patterns, the hardware cost plummets to just 82 adders.
From 110 down to 82.
Yeah. That is a massive 25% reduction in actual hardware.
What's fascinating here is the cascading effect of that 25% reduction. You know, we aren't just talking about saving physical space on the silicon, though obviously that is important.
Right.
We're talking about a 25% reduction in power consumption and a 25% reduction in thermal output.
Wow.
For a mobile device or like a satellite in orbit, that kind of efficiency is revolutionary.
Okay, so if you're listening to this and you're building a system, you now have this super efficient multiplierless mathematical toolkit.
Yes.
We've replaced the 32-pack of sodas with clever smaller packs, and we've ruthlessly eliminated duplicate work using cross CSE. We've stripped away all the brute force.
We really have.
But this is where we hit the central fork in the road of the whole presentation.
Right, the core debate.
Yeah, because the developer presents 2 radically different architectural ways to wire these super efficient building blocks together.
Yeah.
And those are direct form and transpose-form.
Yeah, and architecture dictates how data flows through time and space on the chip. So let's start by analyzing the direct form.
Okay, so looking at the schematics they provided, direct form takes one single data input and it outputs N parallel wires.
Right.
So for our 32-tap filter, that's 32 separate outputs, streaming data out simultaneously. But here is the part that really tripped me up.
What's that?
It has no clock. It has no reset mechanism. It has absolutely no registers. It is entirely composed of just combinational logic.
Yeah. Let's pause and define combinational logic for those who might not spend their days designing circuits.
Please, that would be helpful.
So combinational logic means the circuit has absolutely no memory. It reacts instantly or, as instantly as the physics of electricity allows, based purely on whatever the current input is.
Okay, so no memory at all.
Right. The moment the input changes, the output changes. It doesn't remember what happened even a microsecond ago.
Which means the direct form design doesn't actually finish the job.
No, it doesn't.
The slides explicitly state that to make this function as a real working FIR filter, the user must add their own external shift register and their own external accumulator.
Exactly.
And just for the uninitiated, a shift register is basically a conveyor belt that remembers past inputs, and an accumulator is just the bucket at the end that adds all those parallel signals together.
You've got it perfectly. The direct form essentially acts as a massive parallel calculation engine. It computes all the shift and add equivalents for every coefficient at the exact same time from the same input.
And then what?
And then it just hands you those 32 raw electrical signals.
Okay, I have to push back on this design philosophy a bit.
All right, let's hear it.
Wait, so direct form basically hands you a box of raw materials, just sparking wires, and tells you to finish the job yourself.
Essentially, yes.
You have to build your own conveyor belt. You have to build your own bucket. Why would anyone ever want to use this?
It sounds counterintuitive, I know.
It sounds like buying a brand new house and finding out you have to install all the plumbing and wire the circuit breakers yourself. Like, why not just buy a fully finished plug-and-play version?
It definitely sounds like a massive headache if your goal is just to get a standard filter up and running as quickly as possible.
Right.
But to understand its value, we first have to look at the finished product you just mentioned.
Okay.
In this presentation, that finished alternative is the Transpose-Form.
Right. Yes, the Transpose-Form, which the developer actually notes, is the new default setting in their code generation tools.
And it's the default because it solves the exact complaint you just raised.
Okay, tell me how.
The Transpose-Form has a single unified output, not 32 raw wires.
So the bucket is built in.
Exactly. It has what they call pipeline sum registers built right into the architecture. It operates on a standard clock, and it features an active low reset.
Let's clarify those terms really quick. The active low reset basically just means the system resets itself to 0 when the reset wire receives a 0 signal, and it runs normally when it receives a 1.
Right, which is a very standard hardware convention.
Okay, but the pipeline sum registers,
Mm-hmm.
how do those actually work? Like, where are they?
This is where the structural genius really happens. In the direct form, the input travels down a delay line your conveyor belt and gets multiplied by the coefficients.
Okay, got that.
But in the transpose form, the structure is basically flipped inside out.
Flipped inside out.
Yeah. The input is broadcast to all the multipliers simultaneously. There is no delay line for the input at all. Instead, the delay lines, those pipeline sum registers, are placed between the adders.
Wait, so the intermediate math is what's being delayed, not the original input.
Exactly. You are holding the running sums in little buckets between clock ticks. And to make the math actually work out, the transpose form applies the coefficients in reverse order.
Oh, that is wild.
Yeah, and by flipping the order, the oldest input data reaches the final coefficient at the exact same moment that the newest input data reaches the first coefficient.
So they cascade together perfectly.
Perfectly.
And that creates what the slides call a one-cycle pipeline latency.
Yes.
Meaning you put data in, the clock ticks once, and the fully finished accumulated output pops out the other side.
It's beautiful.
You literally just drop this module into your design, connect your input, hook up your clock, and it just works. You don't have to build any external buckets or conveyor belts at all.
It is entirely self-contained.
Which brings me back to my earlier frustration.
I had a feeling we'd get back to this.
If the transpose form is this perfect, elegant, self-contained pipeline, why does the direct form even exist in this 2026 update? Like, why is the developer bothering to maintain this box of raw wires?
Well, if we connect this to the bigger picture of systems engineering, we have to remember that context dictates design.
Okay.
There is really no such thing as a universally perfect architecture. There are only architectures that perfectly fit specific constraints. So let's look at the specific use cases where that box of wires is actually superior.
All right, I'm listening.
You choose the direct form when you explicitly need access to the raw data before it gets swallowed up by an internal pipeline.
Give me an example of when I'd want that.
One major example the developer gives is building multi-rate or polyphase filter structures.
Okay, polyphase filters.
Yeah.
That sounds like deep sci-fi jargon right there.
Right.
We definitely need to explain the mechanics of that.
Let's say you are building an audio system, right?
Right.
And you need to downsample a high-definition audio stream into a lower quality stream to save bandwidth.
Like compressing an audio file.
Exactly. You might be intentionally throwing away every second or third audio sample. Now, if you use a fully baked transpose-form filter, that internal pipeline is stubbornly going to compute every single step of the math for every single sample.
Even the ones you're throwing away.
Even the ones you plan to throw in the garbage a millisecond later, so you are just burning power calculating outputs you literally do not need.
Oh, I see where this is going. Because Transpose-Form hides all the intermediate math inside its pipeline, you can't tell it to skip a beat.
Precisely, it's an all or nothing system. But a polyphase filter splits the workload into different phases.
Okay.
And because the direct form just gives you the raw, instant mathematical products without any forced delays, a polyphase system can grab exactly the tap products it needs, exactly when it needs them, and simply ignore the rest.
So it is vastly more power efficient for that specific task.
Vastly more efficient.
That makes perfect sense, actually. And the presentation also notes that the direct form gives you absolute visibility, which makes it incredible for debugging hardware.
Oh, debugging is huge.
Right, because you can probe every single coefficient's output in real time with an oscilloscope or a simulator. And you just can't easily do that when the data is buried inside a pipeline.
Your analogy of the house was good earlier, but let's tweak it a little bit.
Okay, keep going.
You buy the pre-built house, the transpose-form, when you just want to move in and live your life.
Makes sense.
But you buy the empty lot with the raw timber and pipes the direct form when you are an architect trying to build a custom skyscraper that needs a highly specialized foundation.
I love that. I really love that. And it perfectly sets up the core mantra of the whole presentation.
Yes, the quote.
I actually want to read this quote directly from the developer slides because it ties this entire architectural debate together so well.
Go for it.
It says, same coefficients, same CSD, same CSE, different structure, different trade-offs.
That is a profound engineering truth right there.
It really is.
Because whether you choose the custom control of the direct form or, the plug-and-play ease of the transpose form, you are still inheriting all the 25% hardware savings of that multiplierless math.
Right, the foundations are the same.
Exactly. The foundational building blocks, the CSD shifts, and the CSE shared patterns are identical. The only variable is how you choose to organize those blocks to solve your specific problem.
But, theoretical architecture is really just a whiteboard drawing until you actually try to compile it into code.
This is very true.
And hardware theories have a notorious habit of crashing and burning when they meet reality. So, did the developer actually manage to get this running in real usable code?
They absolutely did, and honestly, the cross-platform implementation is remarkably robust.
Really?
Yeah, the developer created and currently maintains open source tools in both C++, which is a project called Multiplierless CPP, and in Python, which is a program simply called Multiplierless.
What caught my eye was the strict parity between the two tools.
Yeah, that's rare to see.
Because both projects are driven by a simple JSON configuration file. You literally just type an option, form::direct, or form::transpose.
Just a single line of config.
Yeah, and behind the scenes, the C++ engine uses a library called CSD-CPP, and the Python engine uses one called CDigit.
Right.
But both engines run the exact same cross-CSE algorithms and generate identically perfect CSD quantized hardware code. Like, it matches perfectly.
And that parity is so critical. If you are a hardware team, you need a guarantee that your code generator is going to produce mathematically valid hardware descriptions, regardless of whether your backend infrastructure is built on Python or C++C.
But you can't have one giving you a slightly different result than the other.
Exactly. But you can't just trust the generator, right? You have
Okay.
to actually verify the output.
And their verification methodology is incredibly rigorous.
It really is.
They test both the direct and transpose architectures using automated self-checking test benches.
Okay, let's get into the weeds here.
So they use a tool called Iverlog, which is a standard open source hardware simulator, and a framework called Code.
Right.
And for those unfamiliar, Code is essentially this brilliant bridge that lets engineers write their hardware test scripts in Python instead of wrestling with clunky, archaic hardware verification languages.
It saves so much time. And the way they structure the test perfectly reflects the architectural differences we just discussed.
How so?
Well, for the pipeline transpose form, they fed an impulse signal into the filter and tracked it across 33 clock cycles.
Because it operates on a clock.
Exactly. And it perfectly passed all 33 checks, proving the pipeline operates flawlessly over time.
But for the direct form, the testing looked entirely different.
Right, because of how it's built.
Because direct form is just combinational logic with no memory and no clock. You don't test it over time.
You can't.
Right. So instead, they fed 4 distinct static input values into the system and simultaneously checked the raw output across all 32 taps.
Just instantly reading the wires.
Exactly. And 4 inputs times 32 taps equals 128 separate mathematical checks. All 128 passed perfectly.
It is a definitive mathematical proof that the underlying CSD and CSC algorithms are rock solid across both architectures.
Here's where it gets really interesting for me, though.
Oh, yeah.
Yeah, because amidst all this high-level mathematical theory, polyphase filtering, and architectural purity, the developer includes a slide entirely dedicated to the gritty, infuriating reality of making this test bench actually run on a Windows operating system.
Ah, yes, the inescapable reality of environment variables.
I laughed out loud when I saw this because anyone who has ever written a line of code knows this exact pain.
We've all been there.
You've solved the physical limits of silicon, you've completely eliminated the need for multiplier circuits, and your system crashes because of a missing Python file.
It's tragic.
It is. And the presentation explicitly outlines 3 highly specific, basically undocumented workarounds required to get the Cocode framework running on Windows.
What were the specific hurdles they had to document?
Okay, so if you are listening to this and trying to replicate their work on a Windows machine, you might want to write this down.
Take notes, people.
First, there is a known issue with the system failing to locate the Python dynamic link library, or the DLL.
Classic Windows.
Right.
Yeah.
So you have to manually force the path by setting an environment variable.
Yeah.
pyg pi python bin equals python.exe.
Okay, that's one.
Second, the Verilog code generated by the tool won't actually compile properly on Windows unless you open the file and manually prepend a timescale compiler directive.
Wait, really? What's the directive?
It's specifically tick timescale 1 nanosecond / 1 picosecond. And you have to do this so the simulator actually understands how to measure time.
Oh, wow. Okay. And the third?
The third is a versioning trap. If you're using Kokoba version 2.0 or higher, the old tutorials will tell you to use an environment variable called moddle.
Oh, I've run into this one. That will fail.
It completely fails. You have to explicitly use the updated variable name, which is Kokobi test modules.
This raises an important question about the reality of technology development, honestly.
How do you mean?
Well, this slide proves that in the real world, hardware verification is rarely just about whether your math is flawless.
Right, the math was perfect.
The math was perfect, but often the biggest barrier to entry is wrestling with your operating system's undocumented compilation quirks and weird environmental configurations.
The developer even notes that they've immortalized this entire frustrating setup process as the Kokoba for Windows agent skill.
That's amazing.
They basically took their battle scars and documented them to save future developers hours of agonizing troubleshooting.
It speaks volumes about the maturity of the project. You know, they aren't just presenting theoretical academic slides here. They are providing the exact runner skeletons, the test benches, and the environmental hacks needed to actually deploy this technology in a production environment today.
So what does this all mean? We've talked about grand pianos, canonical sign digits, 30 packs of soda, pattern recognition, and Windows DLL errors.
And it's covered a lot of ground.
We really have. But why should you, listening right now, care about the intricacies of multiplierless FIR architectures if you aren't an electrical engineer?
Because the underlying principles we've discussed today extend far beyond the boundaries of silicon chips.
I completely agree, because whether you are writing software, whether you are structuring a team at your company, or even just trying to organize your daily routine, understanding how identical foundational elements can be structured differently to serve entirely different needs is a masterclass in systems thinking.
Absolutely.
The building blocks are exactly the same, but the Transpose-Form gives you plug-and-play ease of use, while the direct form gives you raw, granular control. You really have to critically analyze what your system actually needs before you start building.
And there's an even deeper philosophical lesson here about how we approach heavy, complex problems.
Oh, I like where this is going.
Think about it. We spent this entire deep dive exploring how engineers just refuse to accept the cost of brute force multiplication.
And just said no to the grand pianos.
Exactly. They stepped back, they changed their perspective, they found shared patterns with CSE, and they realized they could achieve the exact same mathematical result with simple, elegant shifts and adds.
They figured out how to move the piano without breaking their backs.
Precisely. They engineered a mechanical advantage. So the provocative thought I'd leave you with is this. If we can optimize microscopic hardware by stripping away exhausting brute force math in favor of clever pattern recognition,
Yeah.
where else in our complex systems or even in our daily decision making are we stubbornly relying on brute force? Where in your life are you burning unnecessary energy, taking 15 agonizing steps forward when a simple shift in your architecture would let you leap straight to the solution?
I love that. I really
Yeah.
love that. Sometimes the answer isn't to push harder, it's to design a better architecture.
Keep looking for those patterns.
Keep looking for the patterns.
Yeah.
Well, until next time, thanks for taking the deep dive with us.